Alright, are we live? Let's see, hello. Hello, 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 hello. Nice. Oh, I'm very tired. So we're here. Welcome. Let's get right to the next problem. We'll just keep going. Let's keep going. Alright, sparse matrix multiplication. Let's see. What do we got here? Sparse matrices A and B return the result of A and B. May assume that A's column number is equal to B's row number. Oh, no kidding. Oh, matrix multiplication is interesting. It's expensive in terms of asymptotic time complexity. In fact, you could take a look at matrix multiplication on the Wikipedia, and you'll find forgive me as I mess around with my teeth because I had a bunch of food and I guess some of it's sort of stuck in my teeth. But matrix multiplication basically has computational complexity. It's expensive. So in 2020, this algorithm is modified to 2.3728596. 2.3728596 time complexity. Yeah. Yeah, so basically matrix multiplication can be hard, right? So computational complexity of matrix multiplication. Pretty interesting. Really, 2020 they figured something out. It's pretty close to O of n squared log n. Pretty wild. But anyway, yeah, there's matrix multiplications. Not cheap, I guess is my point. So I'm not going to bother trying to come up with a fancy algorithm. We're just going to do a regular old algorithm. Not really regular, just plain old, something that doesn't have, something that's not very, what's the word, not very clever. Not think too hard about this. I don't know if it matters if they're sparse or not, you know. Maybe there's something you can do if they're sparse to optimize, but I don't want to bother. So, matrix multiplication, basically you have, at each point, you have the, if you're familiar at all with row or, if you're familiar at all with like vector dot products, it's basically the dot product of two vectors. So at each index I and j, it's the dot product of the ith row with the jth column. Yeah. So we'll do that. Row. So for each row of A, you're going to loop through each column of how does this work? So for each row, we're gonna have a, how do I? Say new row. And we're going to say for the column 0 to column is less than the number of columns is going to be b dot b of row dot size. It's actually a little more complicated than that. It's let's do it this way. Let's do a row, right? So we're going each row of A, and we're actually going to do for each integer a column. It's really going to be interesting. I've actually not really had to multiply matrices before like this. It seems kind of easy to do, but actually the mechanics of it's like a little bit awkward. It's B row, or yeah, B row. It starts from 0, so yeah, top row, and then it's going to be to b.size b row. And it's actually going to be calculating this dot product. Accumulating this dot product. It's going to be A times B. It's A of A row, whoops, times B, A of A row, times A of A column, or A column, times B of B row, and the column is I think A column, A row, each column corresponds to the other row. Yeah, that's interesting. It's this column is going to be this row, column, row, and this column is going to be actually I'm really confused now. So there's this big outer loop that you do for each row. And then once you've picked a row, then you do each column in that row. You're going to iterate this column and this row, and the next column and the next row. However, I think it's A row is what you pick for the what is this B row then? What is that? Oh, that's so confusing. This is insanely confusing. A row corresponds to B column. So this should be A row. And I'm just utterly confused. Yeah, which row corresponds to which column? Yeah, same column. However, the columns you loop across here and the rows you loop across. Oh, that's just so confusing. Is this right? Am I crazy? Am I doing this right? This doesn't feel right. Is this right? This can't be right. What am I doing here? There's no way. Oh boy. There's no way this is right. Okay, yeah, I was gonna say. It's like, what is going on here? No. Oh no, man. This is bad. Why am I having such a hard time with this? You are going to loop over every row. And for each row, you have a column that you multiply. By. So A row, and then each of those you're going to have a B column that you're actually multiplying by, and this is B of A row dot size. So you pick a row, then you have a bunch of columns, and once you've selected your column and your row, then you have this B row that you increase. So you have A is right. Now you have this B row. Select your column, select your row, select your column, and now you're going to loop over each value in the column, also as you loop over each value in the row. So that's, the row doesn't change. This B row value changes though. And then the last value stays the same. This is the B column. Yeah, now this A row and B row are basically the same. This is A row 2, we'll call it. Or A column, we'll say it that way. There we go. That's what we want. Yeah. And then you do B row, A column. If that makes you feel any better. That's what it's supposed to be. Yeah, that's why it's confusing. It's because it's kind of tricky to get it right. Yeah, that's. Let's try it. Let's see how we do. Oh, nice. Really? Why would that happen? Runtime error. What? 3 rows by 2 columns times 2 rows by 2 columns. But this one works, but this one doesn't. Uh-oh. 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 Row, column. Pick a row A. Oh man, talk about confusing. Talk about confusing. So yeah, there are 3 rows for A. So we should end up with 3 rows for B or 3 rows for C. We have 2 columns for A and 2 rows for B, and 2 columns for B. So we get 3 rows from A and 2 columns from C, gives us 3 rows for A and 2 columns for B. You pick a row, then for the row you're going to pick a column for that particular row. No, this doesn't work. It's actually the column size. It really should just be B of 0, I think. Yeah. This is actually not related to it's not the row here, it's, this is actually the, this is actually only related to, it's not related to A at all, it's only related, it's related to the, it's not even related to, yeah, it's not related to A at all, actually, it's only related to the number of columns in B, which you can only get that from, yeah, from B, from information from B. That's interesting. How do we do? Okay. This is kind of sick, this one. This is like, that took me almost 21 minutes to do something that's actually pretty simple. A better subroutine probably would be like to just do a dot product subroutine. That would be easier to kind of handle this properly, do this, code it up quickly. Let's just do, and we're not going to do any balance checks or anything. We're just going to say row column. We would say int ret equals 0 for int I equals, or r equals row, or no, so it's going to be the row of A and the column of B. So really you have this I equals 0. Could just say like I equals, or A and B, something like that. Where A is going to loop from, for that row, it's going to be the number of columns. It's going to be A of that row, that size, that goes columns, and B is, on B, it's the number of rows for that column. And increment A, increment B. And you have ret plus equals A of that particular row from A times B of B times that particular column. I realize it's super confusing. Yeah, particular column for B. And actually this is the rows of B, and this is the columns of A. Yeah, if you can imagine that. And then now you say, let's push back this dot product of A row and B column. I think that's not just like, I think that's better. I think it's a lot easier to understand and code. It's a lot cleaner. I mean, I realize you could, technically you could even just do like references. Well, the problem with this is the rows, you could have a reference to the vector, but the column, having a column reference is kind of awkward. Like you need like a column iterator or something in order to do this with just like a column vector, I guess. Yeah, a few things to say about this is a lot cleaner to understand, and I should say it's very interesting. Yeah, I think it's easier to do it this way, to kind of think it through and code it up. Like this is supposed to be a really simple, really easy thing. It's literally just each sort of ij index for the matrix consists of the dot product of that particular row column for that ij. So of the result, and yeah. You could technically dump the that column into a vector for temporary use, something like that. I could try that, and that way you could make this just 2 iterators. Give that a shot. Let me see what that does. Let's try that. Call it vector int iterator. And we'll say it's row. And column. And then we'll say I don't know if this works. Try to do this iterators. Something like this. And then you can say yeah. Basically convert the column vector to just a vector you can handle. Be of the rows change, but the column doesn't, right? Which is B column. So we get this B column. I want these rows, right? And we would do it this way. And then now we would dot product of temp begin, temp end, and the other one is row begin, row end. I have a row. Yeah. Kind of just doing this for legibility's sake, just so it's a little bit tighter, you know, so it's not just like flowing off of the side, the right side over here. Excuse me. Really? Why? Why can't we? Oh, I know why. That's why. I know why. Wrong answer. Nice. Sweet. Oh, yeah, that's probably has something to do with it. This should be slower, I think. Oh wow, it's a lot slower. Yeah, because we're creating this extra vector in between, so that we can have a nice, simple dot product routine that handles, iterates over this. Yeah, because you would have to make like a custom iterator class that iterates over the column, something like that. Yeah, it's in order for to really make the logic for the dot product be really simple. Otherwise, I would say just do int row, int column, and then you know it's sort of x equals 0, we'll say. X is less than x is going left to right over all the columns of this row. And x is going top to bottom of all the rows of B. And it's going to be A of the row x times B of x times the column. And you could do it this way instead. And if you do it this way, it's faster, it's simpler. Also, you can just do row or R and C here too. Makes things a lot simpler as well. That's a lot simpler too to follow. Yeah. This part's kind of tricky. When you pick the column, so you have the row, you pick a row. The columns you pick are right. It's actually the size of the row, not the size of the row, but the size of the first row in the matrix, the second matrix. That's like a tricky little thing because You actually don't have an obvious way to get the column size because vectors are variable. Like this matrix is inside a double vector, which means you're assuming that all of the vectors have the same size. So you have to actually pick one of those vectors out to get the size. So I usually just pick the first one here. But there's actually like a little bit of room for, if you fuzz your programs, you give all kinds of random inputs. If you fuzz this, you can actually come up with a problem. You have to do some sanity checks on A and B. You actually would want to do a check that ensures the data looks like it's supposed to look for A and B. But I think this would be the best way to do it really quickly and simply. You do have to remember this tiny little hitch where you can't get the size of you can't get the number of columns in the second matrix without something specific. Yeah, but that's matrix multiplication in a nutshell. It's kind of it as far as like making it fast. Obviously, there's an opportunity here to implement one of these algorithms. However, they're probably pretty complicated, so we'll just leave it. I think with sparse matrices, there's probably something you can do too to make things faster as well. 1969, Strauss improved. Oh wow, interesting. All of these have multiplicative constant, the same computational complexity. Interesting. Doesn't make any assumptions on matrix multiplication, except that this complexity is polynomial for some omega greater than or equal to 2. Amazing. Okay, anyway. Neat. What do we want to do? I guess that's it, probably it. How much time we spend? Yeah, a little over half an hour. That's okay. I mean, there's really not a lot to say about it. You know, it's pretty interesting. There's some papers on it. Let's go from there. Let's just go to another problem. So yeah, thank you for watching. Go to the next one.